Welcome to Easy BTech, your guide for BTech and beyond. My name is G. Sampath. I am going to explain the subject VLSI design. Today, we are going to discuss about the topic fan in, fan out characteristics. Right? What is fan in? What is fan out? What are the characteristics in MOS transistors, which are designed by logic gates? MOS transistors are designed by logic gates. Fan in, fan out. Right? Fan in, fan out. Fan in, fan out characteristics. Right? What is fan in? What is fan out characteristics? Let us see this one. The desired speed of a transistor is defined by transistor on off state. Transistor on off state. Right? So it is a speed of a transistor is depend on transistor on and off. So the desired speed of a transistor is defined by when transistor is on and transistor is off, when input signal applied to the gate, and how quickly the output responds. So how quickly the output response of a transistor when input is applied. When input is applied, how quickly the output responds, then it is nothing but the speed of a transistor. So the another parameter is also included to the speed of a transistor. So there are another parameters included for speed of a transistor. So it is another parameter for increasing the speed of a transistor. The speed of a transistor depend on the state of a transistor on and off. The another parameter is included for speed of a transistor. They are so two parameters are here that we are going to discuss today: fan in, fan out. So by using this fan in, fan out, the transistor speed of a transistor, the speed of a transistor can be known by the two another included parameters. So generally the transistor on and off state, then it is the speed of a transistor. The another two parameters also included, that is called fan in, fan out. Okay, let us see this one. The first one is the included another parameter is fan in. You see this one, fan in. Okay, this may be asked in examination. So define the fan in, fan out characteristics of a logic gates or transistors, right? So let us see the what is fan in. So it is also included parameter for it is applicable to the speed of a transistor. So fan in is Number of inputs to the gate is called as fan in. Number of inputs to the gate, okay, logic gate, number of inputs to the gate is called fan in, so the number of inputs that we are connected to the logic gate is called as fan in, let us see. For example, if you take a logic gate, 2 input AND gate, right, 2 input AND gate, number of fan in is 2. You see this one. Let us see the example. A 2 input AND gate, if you see this one, right, it is AND gate, it is a 2 input AND gate. The fan in of this logic gate, so this is AND gate, we can say this one is AND gate, right. So let us take this, A and B are the inputs, so Y is the output. So these two are called fan in, two fan in, right, fan in 2, we can say this fan in 2, two inputs are here, connected to this AND gate. So any logic gate, the input wires or input terminals, which are number of inputs which are connected to this logic gate is called as a fan in. So if it is a 2 input AND gate, number of fan in is 2, right. The next one, the another parameter for increasing the speed of a transistor or logic gate by fan in and fan out. The second one is fan out, okay, fan out. So fan out, this is the second parameter which can define by a speed of a transistor included. This is also included for speed of a transistor. Fan out is nothing but output of logic gate as a input to the other logic gate, other logic gate, or output of logic gate drive, or we can say output of logic gate drive another, okay, another logic gate, another logic gate as input, right. Output of logic gate as a input to other logic gate, or output of, we can say that output of logic gate drive another logic gate as a input, Let us see this one. So we are already known that what is fan in. It is nothing but a number of inputs which are connected to the gate is called as fan in. The fan out is the output of logic gate as a input to the the output of this one, the output of logic gate as a input to many number of other logic gate, another logic gates, right? Another logic gates. So we can take any number. So here, so let us take, for example, this is a NOT gate, right? And this one is a one AND gate, right? And this one is a NAND gate, and this one is a one OR gate, and this one is a NOR gate. So different logic gates are here, which you are connecting as a input from the output of this NAND gate. You see this one. You see this one here. So we already discussed about this fan-in of this gate. So A, B are the inputs. So this is called fan-in. This is called fan-in. Right? Fan-in is 2. Now this one is output. Output of the NAND gate. So it is NAND gate. Okay, this is a NAND gate. NAND gate output. NAND gate output. So output of this gate drive as a input to the another logic gates. So it is connected to another logic gate as a input. So if you see here, how many fan outs are here? We can say 1, 2, 3, 4 and 5. So the number of fan outs of the gate, number of fan out is how many? 1, 2, 3, 4, 5. 5 outputs. Output as a input. Okay, the output of this NAND gate can drive to the another logic gates as a input. So it can drive 5. So 5 number of logic gates as a input and it can drive 5 number as a input to the another logic gate. This is nothing but a fan out of a transistor, fan out of a gate. So any gate is having fan in and fan out, right? Fan in and fan out. So the fan out, we can say fan out is defined. It is the current ratio. You can take the current ratio of so output of this high logic, output of fan out of high logic, high output voltage to the high input voltage, high output voltage to the high input voltage. So fan out for the low logic. So fan out for the high logic, high output voltage to the high input voltage. So fan out for the low logic, right? Fan out for the low output. So it is output of current ratio of low output current to, we can see low output current to low input voltage, right? Low input voltage. If you see this here, so you see this one here, high output current. If you take this high output current as a high input to this, all the gates, right? This one is a high input, right? High input. So this is high input. Here also high input. So high output of logic gate as a high input to the another logic gate. So the fan out this one is a fan out of the gate. Fan out is how many it can be drive the logic gate. It will be depend the ratio of high output current to high input current, right? High output current to high input current. If it is a high logic, the low logic can be drive. The output of low logic can be drive to the another logic gates. So low output voltage to low input voltage. So it is a parameters, two parameters which we can define the speed of a transistor. The included speed of a transistor is depend on fan in and fan out. Right? Let us see the characteristics of how the, if you are increasing fan in, fan out, then what happens, the delay. Okay, then we are saying that speed is nothing but delay, means how much time taken the output, can drive to the another logic gates. Right, let us take this one, the characteristics here. If we take fan in, fan out, okay, this is the fan in of 2 fan in, 4, 6, 8 and 10. Right, this one is a fan in, fan out. So this characteristics representation, fan in, fan out graph, fan in, fan out graph, fan in, fan out graph, you can say characteristics. Right, so fan out is, here it is 2, here it is 4, here it is 6, and if you take this one is 8. Right, so what happens here, it is a fan in or 2, 4, 6, 8 and 10. These are the fan out. So these are the fan out, these are the fan out, these are fan out and fan in, this is fan in. Right, input and outputs. So what happens, the delay, right, so delay is increased as the increasing fan outs. It is 100 picoseconds per gate, it will be as the gates are increased. Right, so this can be defined, if you take the three technologies. One is 0.3 technology, 0.3 micrometer technology, 0.3 micrometer technology. Then the another one is 0.5 micrometer technology, 0.5 micrometer technology. So it is a, if you take the 0.5 micrometer, 0.3 micrometer gate area, right, feature size of the gate, let us take another one is 0.7 micrometer, right, this is 0.7 micrometer technology, 0.7 micrometer gate area, right, 0.7 micrometer. So 0.3 micrometer feature size of the gate, 0.5 micrometer gate size, feature size. These are the feature size of the gate, feature size of the gate, right, length and width. So what happens, as the fan in changes, fan out increased. So fan out increase, it may be the increase the delay, right, increase the delay, it will be like exponentially, right, it will be like exponentially. The first graph, this one is for 0.3 micrometer. As the fan outs increase, then it will be exponentially increased, the delay is exponentially increased. The another one, the 0.5 micrometer, what happens here, so what happens here, it will be increasing the fan outs, the delay will be increased, right. Here also the 0.7 micrometer technology, what happens here, if increasing the fan outs, then what happens, the delay will be increased exponentially. Right, here one point I want to tell you here, increasing fan out, delay of the gate increase exponentially. So increasing fan out of the gate, right? Increasing delay of the fan out, delay of increasing fan out of gate, increasing fan out of gate, then increasing delay, increasing delay exponentially. So delay also increasing exponentially. So if you are increasing the fan outs of the gate, so delay also increase. So it may be depend on the speed of the gate. So fan out is depend on fan in. So fan out is depend on delay of the device. So delay of the device, delay of the gate, depend on delay of the gate. So it is nothing but speed. So it can be the performance of, so it can be performance of the speed of a transistor, speed of a gate. So it can be influence, it can be influence the speed of a transistor, right? So delay, as less delay, speed increase, delay increase, speed reduce. So this is the means delay reduce, speed increase, opposite, right? Delay reducing, speed increase means time taken process. If it is delay more, then speed will be decreased. Like it is an inverse relationship with as the speed and the delay, right? So it can be influence the speed of a gate, speed of a logic gate. You can say it is speed of a logic gate, right? You see how it will be the logic gate speed performance depend on this fan in, fan out, right? Fan in and fan out. So if you see here, so mostly we are using CMOS logics, right? So we are using different logic families we are used in IC technology. So in IC technology, logic families are, we are using different logic families, right? We are using different logic families. The logic families are, if you are using CMOS technology, is a low power and high speed technology, low power, low cost, high speed technology, CMOS technology, logic families, and TTL is also one of the logic family, and emitter coupled is also one of the logic family, right? If you see this one, the different logic families and ICs are used for the gates and different applications, right? If you are using mobile applications and home, medical, in like we are using in military applications. So all these logic IC, CMOS, TTL and emitter coupled are used, right? If you see this one, three logic families, three logic families let us see this parameter. I want to tell you one or two. First one, we see the fan in. So how many fan in and fan out, fan in, fan out, and the logic 0. Let us see logic 0 and logic 1. Let us discuss these parameters. In different logic families of ICs are there. Logic families of ICs, logic families of IC circuit, ICs, right? Logic families of ICs. So fan-in, by using CMOS, it is a complementary metal oxide semiconductor. Both PMOS and NMOS are there. It is designed by both PMOS and NMOS. CMOS is designed by both NMOS and PMOS. NMOS and PMOS, right? Both NMOS and PMOS. So TTL is used bipolar transistors. Bipolar transistors. Here also emitter coupled also bipolar transistors. So bipolar transistors, right? So by using this fan-in, the number of fan-in for this CMOS is 10. So mostly we use 10, up to 10. So it is used 8 and it is used 5. The fan out, so CMOS having so more number of fan outs. It can be drive more number of logic gates. So up to 50. So 50 outputs, 50 from single output, it can be drive 50 logic gates as a input, right? It may be up to 10 only, right? It may be up to 10 only, right? If you are the logic gate voltage, so how much logic gate? The logic gate 0 is, the voltage is 0 volts to, we can say it is 1.5 volt. It is 1.5 volt. In TTL it is 0 means 0 volts only. But emitter coupled logic it is minus 1.9 volts. Right? In the logic 1, it can be operated the CMOS logic. The voltage level, it will be 3 volts to up to 18 volts. 3 volts to 18 volts. It is 5 volts only. Right? 5 volts. Now it will be minus 0.9 volts. Minus 0.9 volts. You see here, so CMOS is a dominant technology, low power, right? Low cost, the cost wise, so low cost. So cost is, it is a low cost, low power, okay, low cost. This is also low cost. This is also low cost. And this is high cost, designing of this bipolar transistor in emitter coupled logic ICs, right? High cost based circuit. So conventionally high speed, and speed it is high speed. We can say it is if you take here, it is a cost. The another parameter also cost and high speed. So speed also high speed, low power, low cost in CMOS technology, right? TTL and high speed we won't use this. Nowadays we are not using this emitter coupled. So we are using the CMOS technology, low power because of low power, low cost, low power technology. So it is low power technology, right? So like it will be that high power is used. This is also high power is used than the CMOS. Okay, so low power CMOS technology, and also it is more fan-in fan-outs. More fan-in fan-outs. So high-speed signals can be transmitted by using CMOS technology. Applications, logic families, we already seen applications. Applications which can be used in mobile communications, mobiles, right? In communication system, applications, mobiles, communication system, right? Communication system. Okay, communication systems, military, medical, right? All these ICs are used. All these ICs are used in medical applications, right? In military applications, okay, military applications, right? We used these ICs. Right? The ICs are designed by the CMOS technology, CMOS logic family, transistor logic family, and emitter coupled logic family. So more fan-outs are there. It can be drive more number of output as a input to the logic gates. Right? If you see the CMOS technology, ICs which are designed by CMOS ICs are, it can be 40XX series ICs. 40XX series ICs, right? In TTL, the ICs are 74XX series. 74XX IC series are used, right? 74XX series are TTL, transistor logic ICs are used for different applications for analog and digital applications, analog and digital applications, digital, okay, analog and digital, and mixed applications, mixed applications also we can use this TTL and CMOS, right? Here also analog and digital, analog and digital, okay, and also mixed applications also we use ICs, 40xx series ICs, mixed applications we can use, right? Mixed applications also we can use, okay, mixed applications, right? This is about the logic families, the two important logic families which are used in medical, right? In military applications, communication system, the ICs are which are used low power, high speed signal transmission, right? The chip area is also low volume and low size, right? So today we discussed about this fan in fan out. So it is also one of the parameter which is used for increasing the speed of the transistor, right? Fan in is number of inputs, so indicate two inputs, single output. And if you see the fan out of this NAND gate means output of this one, it can drive as a input to the logic gates, so then here 1 2 3 4 5, so as many we can use, right? So the fan out is depend on this current ratio, high output voltage to high input voltage. Then low fan out, low output logic is low output current to low input current. Next we are seeing the characteristics, fan in and fan out. So delay of the gate increase with the 5 micrometer, 0.5 micrometer, 0.3 micrometer, 0.7 micrometer used in CMOS ICs, analog and digital, right? Analog, digital, and mixed applications, are used. Mixed applications, we can also use this technology. 0.3 micrometer feature size of the gate, we use WP-ROM, right? WP-ROM, and it is a 0.7 micrometer. It is used in image sensors, right? Image sensors. So sensing the image, 0.7 micrometer pixels, right? So the mobile application, this is mobile applications. If you see this one, as the delay increase exponentially as the fan outs are increased. So the performance of a gate, the performance of a IC is depend on fan in and fan out. You see, we already seen that different types of logic ICs are used, CMOS, TTL, and emitter coupled, fan in, number of fan ins, number of fan out. In this, the most fan out is used CMOS technology, low power technology, and it can be operated. The logic one is high voltage. So featuring, it can be increased. The logic one is 18 volts. We can say 20, 30 volts, 40 volts also we can increase this volt. It can be drive so many number of outputs, right? So these are the IC representations of CMOS and TTL, right? So thank you. So please subscribe our channel, like, inform to your friends. Thank you.